Ready when you are.
Okay. All right. Our first speaker is one of the resident number theorists. I've known him since his first day as a transfer student from UCF. By the way, thanks for enriching our department with your presence. I've had the privilege to listen to a number of his first presentations. Some were okay, and some were really excellent. Some were really excellent, particularly the one that he talked about prime number theory, and when he presented a hearty, celebrated result on the zeros, the number of zeros on the critical line. That was a wonderful presentation. Because of that, I have high hopes for this one as well. It should be equal to and or greater than in terms of at least enthusiasm, if not new material. So everyone give a warm welcome to Camilo Montoya.
Okay, so unfortunately today I'm not going to do no big result. I'm saving that for the semester where real talk actually kind of saw most of it. I proved the Vinograd 3 primes theorem. It's like a precursor to the Goldbach conjecture. It basically says that the Goldbach conjecture is true in all but finitely many cases. But I'm saving that for colloquium sometime in the semester. Today I'm just going to do elementary introduction to analytic number theory. Basically chapter 2 or so, and then I skip around a lot, but so the text is intro to number theory by Apostle. I'm going to be talking about arithmetic functions, multiplicative functions, which I'm just going to write mult a lot, multiplicative functions, and Dirichlet convolution. Dirichlet, right?
Dirichlet.
So, let's start. So, for this talk, since we're going to be discussing mainly arithmetic, aka number theoretic functions, what I'm going to actually use as a definition, of course, is a very celebrated result from Gauss, but I'm going to call it definition / theorem 0, which is just needed. It's the fundamental theorem of arithmetic. I'm sure hopefully everybody knows it, and that's just that there is this unique prime factorization every n, and the naturals, so greater than 1 I guess, n is p1 to the k1, dot dot dot, pr to the kr. Unique representation. Right. I'm not going to talk about that a lot. Definition 1. An arithmetic also number theoretic, and actually you'll see why they're called number theoretic function is a function f from the natural numbers to r or c. And here, unfortunately, Eric, I'm taking n to be 1, 2, 3.
So put the star.
And
Unbelievable. That's not confusing.
does not confuse.
That's not confusing.
Is there a difference between an arithmetic function and just a sequence? A real number is a sequence of complex numbers?
Technically,
Or
no.
is there another property? No?
Eventually, I guess. I don't even think so, no. I guess you could, yeah, like, I'll have other properties like being multiplicative and stuff, which is,
Okay.
homomorphisms of basically for relatively prime numbers, but other than that, like on just face value, yeah, it's the same thing, sequence, on face value. So examples, I'm gonna give you some. So during this talk, it's gonna be short. It's gonna be. I don't plan on being up here a long time. But we are gonna meet a whole bunch of functions, number theory functions. The first one is the great Mobius function, one of my favorite, and it's defined as. So it's from the naturals to actually the naturals, whatever. No, to 0, -1, 0 plus or minus 1. Really. And it's defined as follows: mu of 1 is 1. Mu of n is -1 to the, we're going to call it r, if n is p1 ... pr, and mu of n is 0 if p squared divides n. In other words, it's not square free. If its representation has one of these ki greater than 1, then the Mobius function is 0 there. And so you see what I mean by number theoretic functions. We're defining the function. The function is defined in terms of the properties of n. And specifically the properties given by the fundamental theorem of arithmetic. So that's kind of what we mean by number theoretic functions. Another example is one that we should all know is the Euler-Tauschen function. P of n. So P of n, from number theory class, we all know it has a cool little product formula, which I'm not going to use at all during this presentation. There's 1 minus 1 over P, right? Or 1 minus 1. I don't know, I just saw this right now. I wasn't even going to talk about the product representation. I'm actually going to define it as follows. We're not going to use the product representation at all. I'm just going to define it as the cardinality of relatively prime guys. So 1 less than or equal to r less than or equal to n minus 1 such that n r. You could also see this as the cardinality of a multiplicative subgroup of that. Another notation they use is this little, actually no, just another way to write it. K equals 1 to n of 1 over n, where this guy's a floor function. Another way to write it, this notation you might see is with little prime here. And it's just, I don't know, over k. And this means over the relatively prime guy is mod n. We're going to use...
What?
You could have left the original.
K equals 1 to
No,
n,
I'm gonna
so
use a
that's
bunch
the
of
sum
them.
of 0, 0.
What, this? This?
You have 1 over
correct.
n.
No, yeah. NK, I'm sorry. This, what I had just there is coming right now. So if their GCD is 1,
Yeah.
you count it. But if GCD is bigger than 1, it's 2.
It's
The
0.
floor function of 1/2 is 0.
Yeah. Okay.
That's a very useful representation. And then I'm just going to mention this for fun. So we have the Mobius and Euler's phi function. I'm going to mention this for fun. The partial sums of the Mobius function, it's called the Mertens function. M of n going to be the partial sum of the Mobius function. Basically, this being asymptotic to big O of, I think it's square root of x, or square root of n. This is equivalent to the Riemann hypothesis, although it's already been proven false. This becomes... this the Mobius function, like for n equals 1, 2, 3, becomes like a coin toss.
If this is equivalent to the Riemann hypothesis and this
Yeah.
is false, then that means the Riemann hypothesis.
No, if this is true, it would imply the Riemann hypothesis.
Oh, okay.
Yeah. Well, it would imply the Riemann hypothesis. I'm sorry.
Yeah, bro, go
And
home
this is
otherwise.
just, and it's plus 1, minus 1, plus 0, minus 1, minus 1, plus 1, like, it's just random, and it's like if, for every n you were tossing a coin, and you're just tossing, you're counting how many, different primes divide it, and of course, no square of primes can divide it. What are the merge function? So definition 2, so those are just examples. Is multiplicative functions. So an arithmetic function that is called multiplicative if f of mn equals f of n is a f of n for all mn relatively prime, such that mn equals 1. And that is called completely multiplicative if this holds for all mn. If f is a homomorphism for all mn. This holds for all mn. It's completely multiplicative. Simple examples again. For example, for any alpha, you can define f's of alpha of n to b and to the alpha. And this guy is completely multiplicative. But the Mobius and the phi function are multiplicative, but not completely multiplicative. Just simple, for example, for both of them, actually, this example works. Mu of 4 is, I forgot what it was. Yeah, mu of 4 zeros divided by the square root of prime is not equal to mu of 2 times mu of 2. Which is 1. And same thing for the Euler phi function. Phi of 4 is not phi of 2 times phi of 2. So those guys are multiplicative functions that are not completely multiplicative. And so now, we're finally going to get to the cool stuff. Theorem 1 is the Dirichlet identity function. We're going to call it I of n. So theorem 1 says that the sum, and we're going to see this throughout the whole presentation, the sum over the divisors of a natural number of the Mobius a lot of ways to write this. How do we see this again? Oh, actually, so yeah, for this, I gotta use the kind of cheating here. I gotta use that mu is completely multiplicative, which actually I haven't shown yet. But it's actually pretty easy. It's not hard. So to see this, you define so Mobius of d is 0 if d is divided by the prime of the square. So that, or n. So that we let m, so just suppose, you could, without loss of generality, you suppose that n is just p1 pr. And define m to be p1 to pr minus 1. Then this sum is just the sum over the divisors of m, Mobius of d, plus the sum of the divisors of m, but now I'm gonna plug in the other divisors which contain PR. And then we have the same thing here. Plus, actually, since it's multiplicative, I do mu of PR times mu of D. Mu of PR, since it's only divisible by one prime, is -1, and this is minus the same thing.
That's quick.
Yeah, it's if you use a multiplicative thing.
So, can I ask a
Yes.
question? Okay, so the first one is that the PI that are the prime factors of n are all distinct.
Yes, it has R distinct.
They're all distinct. Okay, that's the first one.
Yeah, because if it's a square, Mobius there will be 0.
And it's multiplicative, but this would be multiplicative only, not completely,
Yes. Mobius is just multiplicative.
just multiplicative.
It's not completely multiplicative.
Okay,
So this only holds for relatively prime guys,
which,
but all of these are they're prime. Yeah. So, hello. So, and so this I function is going to be very important. This I function is also remarked, I guess. I is also multiplicative. I'm writing too big, I should chill out.
Can you prove that? I think it's completely multiplied.
Yeah, I's, yeah, of course, it's only one, it's completely.
Multiplied by 0.
Exactly. So theorem 2 is that phi of n is sum over the divisors of n of mu of d times n over d. And for this, we'll use this definition here. So that phi of n, we're summing over 1 to n, for function 1 over n, k. But now, this is I of n, the guy in the inside of the sum. It's I of n comma k. So it's wait, yeah. No, what am I doing? I'm plugging in. So this thing at n would be that one changes to n comma k, and this is sum of the Mobius. And if D divides both of these guys, then this is just sum. So we have D divides n and D divides k. We're just gonna evaluate this systematically. You're gonna fix a divisor of n. So if you fix a divisor of n, then since that D divides k, that implies that k is qd, for some q, which that is equivalent to 1 less than or equal to d less than or equal to n. I'm sorry, that implies this equivalence. If and only if 1 is less than or equal to q, less than or equal to n over d. Simple. So that we rewrite this guy as, we're fix the divisors in, and that's what we're going to sum over. And then for that we're going to sum over this range now. That's a equals 1 to n over d of Mobius of d. And now this sum doesn't depend on d, But these fixed from out here. So this is just and you just pull it out, and that sum is n over d. Okay, now, so we're going to start seeing a lot of these types of sums everywhere. So sums of this nature, where, so given f and g arithmetic functions, sums of this nature, of this form, this whatever, these types of sums appear a lot, and they're what we call, for f and g arithmetic functions, they're what we call the Dirichlet product. Dirichlet. Product for convolution. So for f and g, h of n defined to be f convoluted with g of n is defined to be exactly this here right here. So you can show that if f and g are arithmetic functions, then h will always also be an arithmetic function. So with this cool notation, this convolution notation, let's see. With this notation, theorem 2 becomes, theorem 2 restatement says that, so actually we need to define, not even define, everybody knows what the identity function is, so theorem 2 becomes phi is equal to Mobius convoluted identity.
By identity, you mean 1, 1, 1, 1, 1, 1, 1. Okay. Without one.
Yeah. Alright. Yeah, identity. And this notation, theorem 2 becomes this. And theorem 3 is just properties of convolutions. And I'm not going to prove them. And it's that they're commutative and associative. In other words, f convoluted g is g convoluted f. And f convoluted g convoluted h is f convoluted g convoluted h. You can see it's because it's symmetric. The sum, for every divisor of d, for every d that divides n over d is also a divisor of n. So it's kind of symmetric. So that this is f convoluted g is also, like you rewrite it as the d over n's, and this is also g convoluted f. Just you just have to switch these guys, but it turns out being the same exact sum. It's kind of like symmetric divisors. So now we go to inverse. So given an f arithmetic function such that f of 1 not 0, then f has a uniquely defined inverse. F has a uniquely defined, there exists unique f inverse such that f convoluted f inverse is I. And I, which is this guy, is called this is called the Dirichlet identity function. So it's not that identity function, ID of n, it's the Dirichlet identity. So you do it by cases. For n equals 1, you're solving the equation. So f convoluted f inverse of 1. Well, this is just f of 1 times f inverse of 1 is I of 1, which is 1. So there's only one choice, f inverse 1 over f. And again, right, f1 not 0. For n greater than 1, for n greater than 1, we just do the same thing actually. We're solving the equation f of f convoluted f inverse of n. This is sum over the divisors of n, f of d times f inverse of n over d. And this needs to be equal to I of, so like this little thing, this is going to show existence and uniqueness after I'm done. This needs to be I of n, which is 0, because n is greater than 1. So that we just write this as, 1 is always a divisor. So you write f of 1 times f inverse of n plus sum over the divisors of n, where the divisor is greater than 1. So this is kind of by induction. We do it for n equals 1, and then for n greater than 1, we suppose that we have defined f inverse of n for n equals all the way to n minus 1. And we just solve this equation. This is equal to 0, so that there's only one choice. F inverse of n is negative 1 over f of 1, sum, e divides n, so that f, it's kind of recursive. F inverse of n uses f inverse of n over d, which falls in the range less than n. It uses them defined recursively. D. You know, by assumption, by hypothesis, all these guys have already been defined. F, because d's greater than 1. D's greater than 1 and less than n. So these have already been recursively defined. So f inverse of n is defined like this, and this shows existence and uniqueness immediately.
That's a triangle.
Any questions?
Yeah, why did you prove that with a triangle?
Yeah, I'm sorry. I'm just. I have such good handwriting. Like on paper, but on the board, my handwriting sucks. Like I'm just trying to do it quick because like I speak faster than I write. So
Now, the Dirichlet identity function.
yeah, that's
this,
erased.
So the assumption is that if you convolve that with any arithmetic function.
Oh yeah, that's nice.
Okay.
That's nice. Yes. So we have these properties. F convoluted G is commutative, and so that arithmetic function, the I of n, this Dirichlet identity, it follows. What we need is for every f convoluted I is I convoluted f is f, right? That's why we're calling it the Dirichlet identity for these convolutions. And this is and yeah, you just compute it. So f convoluted I of any n would be sum over the divisors of n, f of d times I of n over d, but I of n over d is 0. It's 0 for if n over d is less than, is 1 or less, I mean less than 1. It's greater than 1, I'm sorry. And so that the only term that comes into the sum is when d equals n. So when d equals n, this is I of 1, and d is n. So, and this is commutative, so this is also I over that of n. Do you get my explanation?
Yeah.
This is the only term that comes in non-zero here is when this in here is 1, and that implies d is n. So is f of d times I of 1. So that's the Dirichlet identity for these convolutions. And we did inverses. And something for you algebra guys, and the language of group theory and algebra, the set of all arithmetic functions. The set of all arithmetic functions with f of 1 not equal to 0. I don't know how to write it. It forms an abelian group. There's an object. I like to write it like this, and then an abelian category. I don't know. Forms an abelian group. It's actually more. With pointwise addition and convolution as multiplication, it forms what's called the Dirichlet.
Yeah, well, what's the product on this group?
I don't know, so this is convolution, but even more generally, we'll define f plus g of n pointwise, and we'll define f convoluted g as we have already done. As so, and with these operations, this set forms the Dirichlet ring.
It's an algebra of R, C, each other.
So, remember this, or not have it over there.
So wait, this is called the Dirichlet ring, or is this a Dirichlet?
No, it's the Dirichlet ring. This is the ring of arithmetic functions with these operations. Yeah. So quick little definition is definition, the unit function. I told you we're gonna meet at least 10 functions today, minimum. Where you have the Mobius, the mu, Mertens, Euler phi, the Dirichlet identity, the unit function, u of n. U of n is identically 1. In other words, for every n, it's called the unit function. So with this, you define this unit function, then theorem 1, which was that the identity function was I of n was the sum over the divisors of n of Mobius of d. This now becomes I is equal to mu convoluted the unit function. And so what this tells us is that u and mu are inverses of each other. Which is pretty important. And now from this follows directly a really cool, would be theorem 5, Mobius inversion. This is really simple to see, especially in this convenient notation. Mobius inversion says that f of n equal to the sum or the divisors of n of g of d. F is this, if and only if g is g of n is sum over the divisors of n, Mobius of d, f of n over d. So this is simple. You just use this convenient notation. This means f is g convoluted with the unit function. If this is the case, we do the Dirichlet product on the left by mu, implies that f convoluted mu is g convoluted u convoluted mu. It's associated by that property over there, and we get g. And the other direction is identical. Just actually, this is both right. The other direction just goes the other way. If g is if g is f convoluted with mu, then we just convolute with u on the right and associative, and we get the other formula. And so this is called Mobius inversion. Is that a question? This is Mobius inversion. It's just this. So yeah, so f equals g convoluted u if and only if g is f convoluted u. So now earlier, I don't know, how am I doing in time, man? I actually thought this was going to be a lot further.
35 minutes.
Good. You guys don't mind if I go over, right? Either
I kind of expect it.
Yeah, when don't you, right? So we'll go back to theorem 2. Theorem 2 tells us that this phi function, the Euler-Toshin function, was mu convoluted with the identity function, arithmetic identity function. So we know what the inverse of mu is now, so we just convolute with u. On the right, we do a Mobius inversion, and this tells us that, so now this tells us u convoluted with phi is u convoluted with mu convoluted with identity. So this tells us that identity of n, which is n, is in fact the sum or the divisors of n of p of t. So yeah, any n is just the sum of the divisors of p of t. Just convolute with u. This is direct application of Mobius inversion. And there's a lot of cool things. Take the log of this, and you also have that log of n. So actually, I don't want to define this. I couldn't even define it in there. I just came to my head. Log of n will actually be the sum over the divisors of n of this guy called the von Mangelt. Where this guy of n is called the von Mangelt function. Is log p if n equals p to the k, p is a prime, k is a natural number, 0 otherwise. And this is just a computation, seriously, I'm not going to do it though, because I don't feel like it.
It just follows from theorem 0.
Pretty much. Yeah, I told you all this is very straightforward. There's no, it's interesting, like what we're doing is interesting, or what we may be doing is cool relationships, that might be deep, but how we're doing it is very, I think, kind of elementary. It's not using any deep math. Let's see, so we have those cool facts over there. So now we go back to multiplicative functions. And we're on A1. So back to multiplicative functions. This is another theorem that I'm not going to prove. Actually, this follows also directly from definitions. It's left as an exercise of anything. So if f is multiplicative, given f multiplicative with f of 1 equal to 1, or I'm sorry, but yeah, f of 1 equal to 1, then so given an f arithmetic, given f arithmetic with f of 1 equals 1, then f is multiplicative if and only if f of p1 to the k1, f of pr to the kr equals f of p1 to the k1, f of pr to the kr. And 2, f is completely multiplicative. If and only if the same guy, f of p1 to the k1, pr to the kr, is f of p1 to the k1, f of pr to kr. So f is completely multiplicative if it completely preserves the factorization structure of the integers, of the natural numbers. And it's just multiplicative if this one holds. So I'm not going to provide, this proof is omitted, I'm not going to do it. Follows directly from the definition. But I will need it later, I think, so. And not, so this theorem is I'm not going to prove it, this one also, I'm going to use them. They're not, actually this one I think I could prove. So, if f and g are multiplicative, this implies f convoluted g is multiplicative. Why not? So f and g, so f of 1, g of 1 are both 1, so for n equals 1 it holds. So we're just doing, so define h to be their convolution, so we're doing, and we want to show that h of mn is f convoluted with g of mn, of m times n, so actually fix mn such that mn equals 1. Remember, we're trying to show it's multiplicative so that it's a homomorphism for these guys. We want to show this. But this guy is just sum over the divisors of mn, f of n, f of d, g of mn over d. And the whole point is that there's a one-to-one correspondence between, so let D equal AB, where A divides M, B divides N. There's a one-to-one correspondence between these, between the divisors D of Mn and the ABs, where A divides N, B divides N, and we have A comma B equal to 1. I mean, of course, A comma B has to be equal to 1 because n comma n is equal to 1. And these are divisors of n. So m and n already don't share any factors. So that any factors that divide m and n also don't share any factors, and that's a and b. So this is equivalent to m over a, b over n over b is equal to 1. so that this guy here is just, we plug in, so this is sum over the AB that divide MN, which eventually we just write, we kind of play with it, and write the A that divide M, B that divide N. It's actually, there's this one-to-one correspondence there. And everything just factors nicely because F and G are multiplicative, and you get it. Actually, I'm not going to continue this. You just factor, we fix a divisor of A of M. That determines what, if D equals AB, that determines what B has to be. Once you fix a divisor D of A of N with divisor A, and then so this is H of N. I kind of glanced over this. I have the computation here. I can show it to you guys. It's really not hard. Do you guys kind of get my explanation? Because of this, there's a one-to-one correspondence between the divisors of Mn, D, the divisor of Mn, and the AB, such that this and all this holds, and then that allows, and then F and G being multiplicative, everything just splits, and then you get H of M, H of M.
You're just rearranging the
You're just
sum.
rearranging. Correct. So this one is, if F and G are multiplicative, then their convolution is multiplicative. And we also have, I'm already lost track of the numbering. This would be theorem 8. So that one's 7. Theorem 8 is if F and G and F convoluted G are multiplicative, then F is multiplicative. Kind of like a different thing. And also, so I'm not going to prove this, but a corollary of this guy is F multiplicative. A corollary of this theorem and this theorem is F multiplicative implies F inverse is multiplicative. Yeah, and this follows from 7. It follows directly because F convoluted F inverse is I, and we know I is multiplicative. So we have F multiplicative and I multiplicative, which is their convolution, implies F inverse is multiplicative by this theorem. And combining more of these results, we see that a set of F arithmetic, FF arithmetic, with F of 1 not equal to 0, these guys form a subgroup of the Dirichlet. Or the abelian group, actually, I think I defined before. Just
this is with addition.
No, so yeah, just do actually.
If you're saying it's a subgroup of Dirichlet, right?
No, yeah, so let's just do the guy with convolution, the F convoluted G guy. This, the group of these guys. And these are...
Rewrite that.
Huh?
What do you, the set of F convoluted with G?
Not the set, yeah, I'm being lazy. The group formed by F and G, the group of F's with convolution is